Alright, good day to you guys. It's time for us to make a start in our lecture number 7. I guarantee you there will be no interruptions today. So, in the last lecture we were dealing with half-range functions. Are you in or out? Half-range functions. So with half-range functions, the thing is that functions are defined on 0 pi, not 0 2 pi, or minus pi plus pi. So when you have a problem of this type where there's only half a function defined, then you have two options. You have two options. You can either add on what we call the even extension. Okay, the even extension on the left, which means it will be symmetrical about the y-axis. And in this case, you will get the Fourier cosine series. If you add on the odd extension, then you can get the Fourier sine series. If you add any other thing on the left, it can work and generate that same shape repeating itself, but in not case, this will be a sine or cosine series. The whole idea is to obtain the series either even or odd. That's useful. In fact, that's keeping an eye on what's going to come up next in the course. So if you use other pieces of graphs, okay, but just for academic interest, they're not going to help us to solve the problems to come up later. So we're not going into the details of this now. We already have the notes on this. I was doing a problem. I think I finished the last problem we were dealing with in class. So let's take example number 12, which is quite an astounding problem. It says find the Fourier sine series. For f of x equals to cos x on naught pi. Right, so you want to find a series of sine terms which will converge to cos x. That's a nice, interesting problem. Can you write can you write cos x in terms of sine? Sine x, sine 2x, sine 3x, sine 4x, and so on. So let's try to crack that. What is the question where find the Fourier sine series for sine x? How would you do that? Find the Fourier sine series for sine x. Well, that series, infinite series, will consist of exactly one term. Which term? Sine x. It's 1 sine x plus 0 sine 2x plus 0 sine 3x plus 0 sine 4x and so on. It's the same thing. It's itself. But of course, here is non-trivial. So this we have to calculate. So let's try to churn this out with the information we have. So from what we learned for half-range functions, bk will be 2 over pi, integral from 0 to pi, f of x sine kx dx. So that's 2 over pi, integral 0 to pi, cos x sine kx dx. Now you had some of these questions in this type of stuff appearing in the TATS. So you may have messed your hands with this calculation here. But to simplify cos sine, you have to employ the formulas for cos A sine B. Remember we had formulas for cos A sine B. There's compound angle formulas which we derive for cos A sine B, cos A cos B, sine A sine B, and so on. So this one turns out to be 2 over pi, integral 0 to pi. This is half of cos. Oh, actually, this is sine and sine. Sine gives you cos sine. So it will be sine of kx plus x, or k plus 1x. So we can say k plus 1x plus sine kx minus x. or k minus 1 into x, k minus 1 into x, dx. That's the formula. So let's finish this off. Just 1 over pi. Integrate sine k plus 1 will be minus cos k plus 1x over k plus 1. Same here, minus cos k minus 1x over k minus 1. The limits are from 0 to pi. So now let's plug in the stuff we need. It's 1 over pi. I think we should just take out the minus here to make life a little easier for us as we go along. So let's plug in pi. So you'll have cos of k plus 1 pi minus cos naught, which is 1 over k plus 1 minus. Likewise, you'll have cos of k minus 1 pi. You substitute for x minus 1. Again, this time over k minus 1. Then this can be written as minus 1 over pi cos of k plus 1 pi. I suppose you can write this as minus 1 to the power k plus 1. Although we can just jump to the odd and even discussion immediately, but let's just do that as an intermediate step. Minus 1 to the k minus 1 to k minus 1. You know the trick, cos k pi is minus 1 to the k. So if I have cos of k plus 1 pi, minus 1 to k plus 1. It shifts it by 1. So the odd and even thing will take a different meaning now. So if k is odd, okay, let's do odd first. If k is odd, then bk will be equal to minus 1 over pi. So if k is odd, you agree that k plus 1 will become even. K is odd, k plus 1 is even. So minus 1 to the power even is plus 1. Plus 1 take away 1 is 0. You get 0. Minus. Likewise, minus k. So this is odd minus 1, which is even. Minus 1 to the even is plus 1. 1 minus 1 is 0. So effectively, this is 0. If k is even, on the other hand, then bk works out to be minus 1 over pi. This time, if it's even plus 1 is odd. Minus 1 to the odd is minus 1. Minus 1 is minus 2. Minus 2 over k plus 1 minus, again here, minus 2 over k minus 1. Right, so I suggest we take out the minus 2 as a common factor, so you get 2 over pi into 1 over k plus 1 minus 1 over k minus 1. Do your high school stuff here, 2 over pi, the LCD is k plus 1 into k minus 1. That's k minus 1 minus k minus 1. So that gives us, the k's cancel off, so we get minus 4. Is the sign right here? Did I make a mistake with the sign somewhere? Hmm? Yeah. Ah, yes. Okay, yeah, that makes a difference. So here, that's positive, so this becomes positive. We just change those signs there, guys. Otherwise, it'll go wrong. So then you'll get k minus 1 plus k plus 1. Okay, that's better. Yeah, now it's looking more reasonable. I was wondering how this term can have negative numbers to it. So it will become 2k times 4, which is 4k. Hey. 4k over pi into k plus 1 into k minus 1. Okay, so now what it means is that you can then say that the function f of x equals to cos x can be approximated by, or can be equivalent to, in fact, the function 4 over pi sigma k over a squared minus 1 sine kx, and k equals to even. In other words, that's 4 over pi into, when k is even, 2 over 2 squared minus 1, that's 2 over 3. 2/3 sine 2x plus, and k is 4, 4 over 15 sine 4x, etc., etc. So that's cos x. Sometimes it's possible to milk this result for some other accidental mathematical result, like series. You want to add up certain series, like we've done already. What's the amount is for 5? Here, 1 minus 1, what's the sequence? We had 5 over 4 equals to something on the right hand side. That gave us the value of 5. If you try to substitute certain things here, it may work, they may not work. You see, if you substitute, what would you like to substitute here? I told you yesterday in the tutorial that the main suspects are 0. If you're not there, you should make a note of this. 0, 5 over 4. When does 5 over 4 arise? When is the root 2 in the problem? Then 5 over 3. When does that arise? There's a root 3 in the problem. Because cosine of 60 is, sine of 60 is root 3 of 2. Then you can use 5 over 2. So 0, 5 over 2, these are useful ones. If you try putting pi over 2 here, what's pi over 2? Is 0. Right hand side, here it's 2 times pi over 2. So sine of pi is 0. Here is the sine of something pi, a multiple of pi, 0. So you have 0 equals 0. Harmonizes. The problem comes about if you put pi over 2. Suppose you put pi over 2 here. What's cos of pi over 2? Cos of 90. That's not 0. Yeah, it is 0. It is 0. It is 0. On this side here, I have 2 times pi over 2. 5. Here it's 4 pi over 2. Actually, these are also going to be 0. You see that? In fact, it does harmonize. It's fine. No, I said 0. I said 0. Oh, if you put 0 in here, that's when you have a problem. I think I said that, but I substituted pi over 2. If you plug 0 in here, cos 0, that's 1. Now see on the other side. Sine 0, 0, 0. All these 0. So you get 1 equals to 0. How do you resolve that? Why did this happen? How can you explain it? You see, there's a conundrum here. It's a bit of a freaky thing that has happened. It's not that freaky. Have a look at the graphs. Let's look at the graph. Remember, the function is f equals to cos x on naught pi. So if I drew a picture of this on naught pi, the cosine graph looks like that. Pi. This is pi over 2. Now I want to construct this Fourier sine series. So which extension did I add on here? Odd or even? The odd. So then I added on this part here. This is symmetrical about the point minus 0.00. Okay, so this is 1 and this is minus 1. Now, can you see the problem? At 0, what is happening at 0 on the curve? There is a discontinuity. At 0, there's a discontinuity. It jumps from here to here. That's why the thing became wonky. Cos of 0 gave you 1 on this side and 0 on that side. So, at 0, x equals 0, left-hand side equals to cos 0 equals to 1. Right-hand side is equal to 0. Why? because there's a discontinuity at x equal to 0. And the Fourier series converges to what at 0? When there's a discontinuity, a jump discontinuity, you may remember me talking about something called Dirichlet conditions. When there's a jump discontinuity, the function jumps from here to there. Where does it converge to? Remember, it's a sequence. The Fourier series is something like this. Right? And then it jumps up, and then it goes like this. Sines and cosines. It settles down. Where does it converge to at the when you have a jump discontinuity? Converges to 0, which is the average at the jump. This always happens. This is Dirichlet's theorem. Fourier series converges to the average value at the jump discontinuity. In other words, midpoint. The midpoint. All right, so that resolves that problem. You can't do 0 in problem because it's not used. Any questions from your side? When you're not following, you should actually ask and clarify. Don't let me go on for several lectures and then you wonder what happens. I'm very simple early on. It's not to your advantage. And this stuff is quite deep and difficult. You mustn't underestimate it. All right, now we will talk about a new thing. You see, so far we've been focusing on the interval 0 to 2 pi or minus pi to plus pi. I'm sure you must be wondering when you lie on your bed and you think about this complex analysis. What about if you use any other interval, let's say 0 to 5 or 0 to 20? Yes? What? Oh. If you have to go from 0 to 5 or 0 to 10 or 0 to 2, in other words, no mention of a pi anyway. The pi is very convenient because it's trig functions. Multiples of pi give you 0 and some good numbers. Okay? Now, what if we want to change the interval? So let me now deal with change of interval. In other words, any interval. For example, 0, 10. Doesn't have to be pi. Now, for periodicity, the important thing about these functions here is that they are periodic. What that means is that f of x gives you the same answer as f of x plus 2 pi. Or that's if 2 pi is the period of the function. Every 2 pi, you cut and paste the same thing. You can have any other period, or you can have f of x giving you f of x plus 2l, where l is any interval, any number. So you can have the same shape from 0 to 10, just cut and paste all the time. So it's periodic. Now, see what happens when I make a substitution of this type. Observe this here. Replace x by pi x over L. So I will get f of pi x over L. You'll see why this is an inspired choice. There's no mystery behind it. It'll preserve the periodicity. So on the right hand side, we'll have x will become pi x over L plus 2L. And I can take out a common factor pi over L and get x plus 2 pi. In other words, I find that the periodicity is preserved. There is a scale factor of pi over L in front, but for pi x over L, in other words, if I scale by pi over L, whatever the interval length is, then the periodicity is preserved. So you can get the function repeating itself every 2 pi over L. So that should suggest that if you want to change the interval, then so we may change. okay, here I can say periodicity preserved. So we don't violate the periodicity. You can still get it periodic, provided you do this trick of scaling by pi over L. So we may now replace kx by k pi x over L. Then everyone lives happily ever after. It's still a periodic function. It doesn't have to be exactly pi units in length. It could be any length. So then I can write these, let me write our normal Fourier things now in this new language here. So we can say so f of x can be now written as sum of ak cos k pi x over L plus sum of bk sine k pi x over L. K equals to 0 to infinity. And these coefficients, they follow the same kind of structure as what we have derived already. AK, instead of 1 over 2 pi, it'll be 1 over 2L. 1 over, well, A naught. Let's take A naught first. A naught is 1 over 2L. A naught is 1 over 2L. Integral from minus L to plus L, f dx. Interval length here is 2L, by the way. We could even go from naught to 2L, if the question said that. And then the AK will be 1 over L, integral from minus L to L, f cos k pi x over L dx. I trust you can see that this is exactly the same thing now as we've done all along. We're just replacing kx by k pi x over L. And the game goes on as normal. dk equals to 1 over L, integral from minus L to L, f sine k pi x over L dx. Okay, so those are the formulas which I'm just repeating now in the new language of pi over L. It's scaling by pi over L. If you block pi over L, it's the old kx. So the angle, as it were, has been scaled by pi over L. And now any interval can work. Any questions? Anything that you're not convinced by? The secret of a mathematician is to make sure the students are convinced and believe it. It can't be just a dogmatic thing like a, dogmatic. You spray the guy with a bit of doom and say, believe this, it's correct. Like, no. My job is to convince you. It's more like not even a lawyer. Lawyers don't sit so high in the logic tree as we do. We are supposed to prove our statements. Lawyer can convince somebody based on probabilities. We don't believe in such stuff. All right, let's take an example, number 14. I'm going to stick to many of the examples in the book. I don't know if you want me to change to new examples. The reason why we use the book ones is because they are hard enough. And when you sit at home and you read those ones, you wonder how things go from one step to another. It will take you long to figure it out. Therefore, it's good for you to practice those examples by doing it yourself, as you used to learn for your high school math, and then you look at the answer in the book, and you have a clear correspondence. And in class, we just try to explain and clarify what is going on. So we don't do them entirely in detail, but just to make it clear to you so you can understand it. But if you feel that you can manage reading those on your own and we can just take some other examples, we can do that. It's quite easy to make these examples up. Find the Fourier series of period 6 units for the function f of x equals to absolute x squared minus 1, minus 3 to plus 3. That's the question. And you'll see why it's somebody thought, because tutorial yesterday, I discovered that maybe you didn't know how to integrate the web. It's something you've done in first year. What is no, what people see means is repeating itself. But it's no longer repeating exactly 2 pi. In the table, 2 pi becomes pi of L times smaller. Oh no, yes, it's sideways, not the amplitude. The amplitude would be a number in front of sign. This is what I mean. The coefficients are AK and KU. Other questions? All right, yes, I was saying that sometimes it's good to look at these textbook ones because people don't realize how things work. Now, if you take absolute x squared minus 1, what does it look like? Can you draw it quickly without peeping in the notes? What do you think it looks like? Don't worry, I won't come around and check. Have a crack, just to see if you know. Right, so you see that there are two options. The absolute value can either be positive or negative. So the thing inside will be positive, provided the thing inside is positive. So if x squared minus 1 will remain x squared minus 1, provided x squared minus 1 is more than 0. There's an inequality which you learn to solve in the school. That means that x is less than minus 1 or x is more than plus 1. Forgot all that is for first year, first year. Then the interval given there is from minus 3 to plus 3. So you go from minus 3 to minus 1, or on the more than one side, you go from 1 up to 3. It stops. That's case 1. Case 2 is when the thing inside is negative. Well, the absolute value becomes a negative of the stuff inside. If the stuff inside is negative, like the absolute value of minus 5 is minus of minus 5. Becomes plus 5 again, of course. In the end, everyone looks happily ever after that. But there's a step process, minus of minus 5. So this becomes negative of this, which is 1 minus x squared, provided the thing on the inside is negative. X squared minus 1 is less than 10. And when you solve that, it's from minus 1 to plus 1. Okay, it's far away from 3, so forget the 3. So the x's here are minus 3, minus 1, 1, and 3. So the first parabola is x squared minus 1. So you have a parabola like this. Okay, and then you have another parabola 1 minus x squared. So you have a parabola like that. Now the first guy is valid between minus 3 and minus 1. So at minus 3 up to minus 1. So it's valid up to there. The second guy is valid, second piece is from 1 to 3. From here to there. And then lastly, the middle guy is valid from minus 1 to plus 1. This guy here. So this part here is 1 minus x squared. These parts are x squared minus 1. Did you get that? That's what the graph looks like. Another way of thinking of it is that you've got a parabola. If you hit the parabola with an absolute sign, This negative piece here will flip across here. It'll be reflected in the x-axis. That's what has happened. If you don't want to do all this analysis here and breaking it up into pieces and stuff, then you can just argue from your knowledge of symmetry. Have a parabola, x squared minus 1. Hitting that with an absolute means that you are flipping this thing, the negative portion to the top. That's what you get. So now, let's try to write down the Fourier series. The question was to write down the Fourier series for this function here. So bear in mind here, they said that the interval is from minus 3 to plus 3. So we can say the length, 2L, is 6. It's from minus 3 plus 3. So L in this problem is 3. That's the crux of these problems. If it says Fourier series and the interval is minus 3 to plus 3, that's what keeps repeating. So that's 2L. Remember I said the periodicity is x plus 2 pi or x plus 2L. That's 2L minus 6. If you are asked to find the Fourier sine series or Fourier cosine series, you may find that that's 1L. 1L is 6 and 2L will be 12. But we will do some examples to train you how to handle that. All right, so then now we've got this figured out. A naught is 1 over 2L. Is 1 over 6. Integral from minus 3 to plus 3 of f dx. We also know this function is even, by the way. How do we know that? Just by looking at it, you can see it's symmetric about the y-axis. It's even. So you may double this and get 1/3. Integral from 0 to 3 f dx. And when you actually calculate this, it's 1/3 of integral from 0 to 1. That part will be 1 minus x squared dx. And then if you go from 1 to 3, that part is x squared minus 1 dx. From here to here, 0 to 1. From 0 to 1, this is portion here, 1 minus x squared. From 1 up to 3, it's x squared minus 1. All right, so of course, I'm not going to do the whole calculation. That turns out to be 22 over 9. Right, that's a simple calculation. If you turn that out, you should get the answer 22 over 9. This is what I mean by we're not going to do all the calculations from scratch. And we also know this is an even function, so then we only have the cosine part, isn't that so? There's no need to consider bk, we only have ak. So if you work out ak, the formula there was 1 over L, so it's 1 over 3, integral from minus 3 to plus 3 of f cos k pi x over 3. 2L was 6, L is 3. K pi x over 3, that's now the new thing here, dx. And again, I'm not going to crank this out for you guys because it takes a bit of time. I mean, you can double this, 2/3 integral 0 to 3 f cos k pi x over 3 dx. Carry on working this out. Integration by parts, by the way. Well, let me write another line here. So it'll be 2/3. So from 0 to 1, you will have 1 minus x squared cos k pi x of 3 dx. Plus, then from 1 to 3, you'll have x squared minus 1 kicking in, cos k pi x over 3 dx. And no, you won't be able to combine these things. They won't work out well. There are different limits. Can't put them together. In case you don't let evil thought in your mind. They look very similar, but there's no way you can combine them. You can't put a minus sign out here and make it 1 minus x squared. You can, but then it will be from 3 to 1. It's the reverse thing. It doesn't work. So the final answer there, let me just give you the answer because it will take us time to compute this. You can just write down this answer, 72 sine k pi over 3 over pi cubed k cubed minus 24 cos k pi over 3. You can just jot this down for completeness. Doesn't mean much. Pi squared k squared plus 36 minus 1 to the k pi squared k squared. Right, and of course bk is 0 because f is even. If you take even times sine kx, it will be, or even if you take sine k pi x over 3, it's still even times odd. It's odd. Questions? Anything that's not clear? It's a good thing I got another 17 minutes left. What? 15? Okay, I accept. I take your word for it. All right, then what remains for me to do is just to talk about half range in this new language. What does it mean to have half range functions? It's the same thing, the same idea. Half range, you have an even extension and an odd extension. You won't have too many choices here because that's what we want really in the rest of the game. So let me just clinch this point about half range functions. Everyone on the same page as us? If you miss some stuff, it's going to be uploaded, right? Yesterday's or the last week's lecture was interrupted. I'll have to redo it myself at home. I'll do some highlights for you instead of doing the whole thing because fill in the blanks. You didn't record properly. Half range functions. This time we are talking about not L. And there is some ambiguity here, you see. Just because somebody says not 50, you may ask, is that half range or full range? It depends what the examiner says. If he says that it repeats every 50 units, then it's full range. If it repeats every 100 units, then it's full half. That will be clear from the question. Another way it becomes clear is if they say find the Fourier series, then you take it to be the full range. If they say find the Fourier sine, then you take it to be half, or Fourier cosine is half. But you'll see that in some examples. So as usual, you have even extension. You may choose even extension, in which case you'll get the cos series, and then your function will be some ak cos k pi x over L, k equals 0 to infinity, where the a naught will be 1 over L, integral from 0 to L, f dx, and the ak will be 2 over L, integral 0 to L, f cos k pi x over L. You know how this 2 arises? Because these are going to be even. At the end of the day, they're even. So instead of having minus L plus L, we double it. On the other hand, if you were asked to deal with the odd part, so the examiner will say, find the Fourier sine. Then you know we're dealing with the odd part. In this case here, your function f of x will have the shape sigma bk sine k pi x over L, k equals to 0 to infinity. And in this case, bk, of course, only one of these survives. bk will be 2 over L, integral from 0 to L f sine k pi x over L. Oh, not the whole thing. K pi x over L dx. No, not dx. Yeah, dx. That's the integral. Finally, I just make some comments on example 15. I'm not going to deal with the entire example. As you said, you can read it yourself. I'll just highlight some aspects of it. The function has got f of x equals to x for 0, 10. The question is, find A, the Fourier series, B, Fourier cos series, and C, the Fourier sine series. For this function, find B on not 10. So this is where I said that we have a choice here. Well, it's a bit ambiguous when you look at log 10. Is it half range or full range? But if they say find the Fourier series, you treat that as full range. If they say find the Fourier cosine series, then this is half range. Here, 2L is 10. Here, L is 10. Here, L is 10. The formula. I think, let me stop here because I have one more minute. Next time I need to draw this graphs for you and show you how they will repeat itself. Yes.